Good morning. This is Mandeepa from Tara Government Degree College, Sangareddy. In this video, we can discuss one more colligative property, that is osmosis. What is meant by osmosis and what is meant by osmotic pressure? How can we determine the osmotic pressure of a solute of a solution? And what are the rules for osmotic pressure? How can we determine the osmotic pressure value? What is meant by Hoff's rules? How can we implement the Hoff's rules for Boyle's law, Charles' law? And that how can we determine the osmotic pressure experimentally? That which we can discuss it in this video basically. So now we have to go for what is meant by osmosis and osmotic pressure. So osmosis is defined as the spontaneous flow of solvent molecules towards the solution side when both are separated by a semi-permeable membrane. So osmosis is nothing but it's a flow of solvent molecules towards a solution side when both are separated by a. So in general, if you want to perform an osmosis, but the solutions must has to be separated by a semi-permeable membrane. So it's a spontaneous flow when we separate with a semi-permeable membrane. And one more definition which we can say for osmosis. So osmosis may also be defined as the flow of molecules from the solution of generally from lower concentration towards the solution of higher concentration when both are separated by a semi-permeable membrane. So in general, a flow of molecules from a solution to the solution of lower concentration towards the solution of higher concentration when both are separated by a semi-permeable membrane. That means if two solutions are there, one is having low concentration and another is having high concentration. In such that two solutions, if we separate it with a semi-permeable membrane, then in such case, molecules that can be moved or that can flow from a low concentrated solution to high concentrated solution through a semi-permeable membrane. So that process generally, which we can call it as an osmosis. So it's a spontaneous flow only when the two solutions, they must has to be separated with a semi-permeable membrane. That is the main condition for osmosis. So even in the diffusion also the same thing which will happen. Then what is the difference between diffusion and osmosis? It's a slight difference only which we can observe it for the both diffusion and osmosis. So what are the basic differences between diffusion and osmosis, that which we have to know now? So first one is it takes place directly and no semi-permeable membrane is needed. So for diffusion, simply the movement of or the flow of molecules takes place from higher concentration to lower concentration generally. But in case of that, there is no need of any membrane which has to be separated between the two solutions in case of a diffusion. But for osmosis, if the osmosis process, if it has to be performed, a semi-permeable membrane must be present. So it needs a semi-permeable membrane. That is the first thing which we have to observe it, the difference between diffusion and osmosis. The second one, molecules move from a region of higher concentration into a region of lower concentration. So in diffusion, molecules, there is no need of any separable membrane or separable membrane for two solutions. And in diffusion, molecules, it can be moved from higher concentration to lower concentration region only. But in case of osmosis, it's exactly opposite with the diffusion. So molecules from lower concentration to a higher concentration, that has to be moved and through a semi-permeable membrane only. That is the thing which we have to know. And both the solute and the solvent molecules can move freely. In case of diffusion, both the in a solution, automatically the two components which is present in any solution is solute and solvent. So in a diffusion, both solute and solvent molecules, they can be easily moved freely in the diffusion process. But in case of osmosis, only solvent molecules, they can interact or they can move. Or the movement will take place only for solvent molecules in case of osmosis. Next, it is common in gases as well as in liquids. So we can observe the diffusion process both in gases and liquid. But in osmosis, it is restricted to solutions only. Osmosis, specifically it is restricted for solutions only. And for diffusion, it cannot be prevented by applying external pressure. It's not possible to prevent, or it's not possible to stop the diffusion process by simply applying the external pressure. But we can stop the osmosis process by simply applying the external pressure. That is the main difference between diffusion and osmosis. So basically, we have 5 differences between osmosis and diffusion. First one is it takes place directly into a semi-permeable membrane is needed. So no need of any semi-permeable membrane for diffusion, but it needs a semi-permeable membrane for osmosis. And in diffusion, molecules, it can move from higher concentration to the lower concentration. But in case of osmosis, solvent molecules only can move that too from lower concentration to higher concentration region only. But in diffusion, both the solute and solvent molecules that can move freely. But in case of osmosis, only solvent molecules that can be moved freely. And we can observe the diffusion process both in case of gases and liquids also. But in case of osmosis, it is restricted only for a solutions. And we can't prevent the diffusion process by simply applying any external pressure. We can stop the osmosis process by simply applying a external pressure. So that is the main differences between osmosis and diffusion. So if any solutions which are having a what type of how much osmotic pressure has the molecules which are having, and then what is meant by isotonic solutions, that which we have to discuss it now. When two solutions of different concentrations are separated by a semi-permeable membrane, then the solvent molecules flow from from the solution of lower osmotic pressure towards the solution having higher osmotic pressure. This continues till both the solutions attain the same osmotic pressure. So osmotic pressure is what? The pressure which is exerted by the osmosis process is nothing but osmotic pressure. So with the process of osmosis, whatever pressure which is generated or whatever pressure which needs, that is nothing but osmotic pressure. So if two solutions, if they are separated by any semi-permeable membrane, then in the osmosis, the only thing which we have to remember is solvent molecules only can flow. So solvent molecules flow from a solution of lower osmotic pressure to a solution of higher osmotic pressure until both the solutions which have the same osmotic pressure. So a pair of solutions, those which are having the same osmotic pressure, which produce no flow of solvent molecules through semi-permeable membrane, are called as isotonic solutions. So a pair of solutions, that is two solutions which are having the same osmotic pressure, because if they are having same osmotic pressure, there is nothing to be possible to move the solvent molecules from one solution to another solution, because both are having the same osmotic pressure. So the flow of solvent molecules is not possible. So such a type of solution, that means solutions which are having same osmotic pressure, that solutions generally we can call them as isotonic solutions. So isotonic solutions, they are having the same osmotic pressure. So there is no flow of solvent molecules takes place, that are nothing but isotonic solutions. Whatever the laws which we know for a gases, that to ideal gases, that is gas equation, that is PV equal to nRT. The same type of laws which we can be implement, or which we can be obey for the osmotic pressure also. So different types of laws which we have to obey the rules of osmotic pressure, that which we can call it as a laws of osmotic pressure. So what are that laws and how it is related with the osmotic pressure, and what is the ideal equation for osmotic pressure, like gases equation PV equal to nRT, that which we have to discuss is under the laws of osmotic pressure. So Van Hoff was showed that a scientist who expressed the different laws for osmotic pressure, the scientist is nothing but a Van Hoff. So Van Hoff was showed that a parallel relation exists between the pressure exerted by the gas and the osmotic pressure developed by a diluted solution. So there is a small relation, a parallel relation which is existed by a gas which consists of a whatever the pressure which is exerted by the gas, and the osmotic pressure developed by a dilute solution. So osmotic pressure where we can expect it, generally it is for a solutions, that is dilute solutions. So there is a relation or a parallel relation which we can observe. That means Van Hoff observed that there is a parallel relation which is existing between the pressure of a gas and the osmotic pressure of a solution, dilute solution. So what is that relation? That how he explained? He suggested that dilute solutions obeyed Boyle's law exactly in the same way as the gases do. So how the Boyle's law as the gases can obey, and the same way how the gases can obey the Charles law, in the same way solutions also can obey the Boyle's and Charles law, like how the gases that can obey the Charles and Boyle's law. Hence, these laws, when applied to dilute solutions, are called Boyle-Van Hoff law and Charles-Van Hoff law, respectively. So, whatever the laws gases can obey, that is Boyle's law and Charles law, the same type of laws as the solutions that also can obey. So that Boyle's law, simply which for a dilute solutions, we can call them as Boyle's-Van Hoff's law and Charles-Van Hoff's law, because they can obey the same way as the gases, how they can obey for Boyle's and Charles law. So what is Boyle's law? Boyle's-Van Hoff's law. And how can we express the osmotic pressure for dilute solutions based on Boyle's law? That which we have to see now. See, Boyle-Van Hoff's law, what it affects means effect of concentration on osmotic pressure. So in case of Boyle's law for gases, P is directly proportional to C. So that is how the pressure of a gas which has to be affected with the concentration, that is for Boyle's law for gases, and for Boyle-Van Hoff's law for a osmotic pressure. What it affects means it affects how it is affected the concentration on osmotic pressure, that will be explained by Boyle-Van Hoff's law. So it states that temperature remaining constant. So that is nothing but at constant temperature. The osmotic pressure, simply we can represent the osmotic pressure as symbol pi of a dilute solutions is directly proportional to the concentration of the solution. So at constant temperature, osmotic pressure of a dilute solutions is directly proportional to the concentration of the solution. So mathematically, how can we represent that? Means pi is the osmotic pressure. So pi is directly proportional to C. C is nothing but a concentration of the solution at constant temperature. So Boyle-Van Hoff's law, what it explains means, what is the effect of concentration on osmotic pressure? It affects basically, it explains. So based on Boyle-Van Hoff's law, at constant temperature, the osmotic pressure of a dilute solutions is directly proportional to the concentration of the solution, that is based on Boyle's law. So mathematically, we can express that with a pi is directly proportional to C. C is a concentration. Pi is the osmotic pressure. That's to only at constant temperature. Or simply we can write it as pi by C equal to constant. That is, once again, it is a at constant temperature only. Simply we can substitute the C value in terms of volume. So generally, if 1 mole of a solute is dissolved in V liters of the solution, then generally, if 1 mole of a solute dissolved in V liters of a solution, then C equal to 1 by V. C is nothing but a concentration of the solution and V is volume of the solution. So instead of C, if we replace that with 1 by V, then therefore pi is directly proportional to 1 by V. That is nothing but pi is proportional to C. So instead of C, we have to replace C with a 1 by V. So that is pi is proportional to 1 by V at constant temperature only. Or simply we can say that pi V equal to constant at constant temperature. This is more important for Boyle's law, because at constant temperature only, whatever the concentration or a volume which affects the osmotic pressure, which is given by Boyle's-Van Hoff's law. So that at constant temperature only, we have to give that value, that is pi V equal to constant or pi by C equal to constant, that which we can express, which is similar for that of a Boyle's law of gases. So for Boyle's law of gases, what it explains, at constant temperature, the pressure of a gas is directly proportional to the concentration of the concentration of the solution, whatever it is. So that which we have to, pressure of the gas, which is directly proportional to, which is inversely proportional to the volume of the gas at constant temperature. That is the Boyle's law for gases. So which is same with the Boyle-Van-Hoff's law, which is applicable for osmotic pressure. So that pi V equal to constant, that too at a constant temperature, which is similar with the with that of Boyle's law. So hence Boyle's Van Hoff may also be stated that temperature remaining constant, the osmotic pressure of a dilute solution is inversely proportional to the volume of the solution containing 1 mole of a solute dissolved in it. So instead of osmotic pressure is directly proportional to the concentration, we can also express the Boyle's Van Hoff's law in terms of a volume also. So at constant temperature, the osmotic pressure of a dilute solution is inversely proportional to the volume of the solution when means containing only 1 mole of a solute dissolved in it. If a solution which consists of only 1 mole of a solute, then at constant temperature, osmotic pressure of a dilute solution is inversely proportional to the volume of the solution containing 1 mole of the solute dissolved in it. That is based on Boyle's Van Hoff's law. Next one is Charles Van Hoff's law. What it explains means it's effect of temperature on osmotic pressure, which is explained by Charles Van Hoff's law. In Charles' law also it affects with what is the effect of a volume of a gas with a temperature, that is explained with is proportionality in Charles' law. It's the same thing which we can observe in case of a osmotic pressure also, that is nothing but Charles Van Hoff's law. So what it states means, it states that concentration remaining constant. So when the concentration is constant, the osmotic pressure of a dilute solution is directly proportional to absolute temperature. So when the concentration is constant, so the osmotic pressure of a dilute solution is directly proportional to its absolute temperature. So in case of Charles' law for gases, at constant pressure, the volume of a gas is directly proportional to the absolute temperature, that is for gases, Charles' law. The same thing which if we implement for a osmotic pressure, then it turns as Charles Van Hoff's law, which affects on the temperature of a temperature on osmotic pressure. So at constant concentration, osmotic pressure of a dilute solution is directly proportional to the absolute temperature. So mathematically, simply which we can represent it as pi is for osmotic pressure. So pi is directly proportional to T, or pi by T is equal to constant. So that is Charles Van Hoff's law. Next. So first two equations, that is Charles Boyle's Van Hoff's law and Charles Van Hoff's law. If we club these two, then we can expect one equation for osmotic pressure. So that is Van Hoff's equation of dilute solutions. That is nothing but it's just like a ideal gas equation, which we have to expect it. Now, what it affects means simultaneous effect of concentration and temperature on osmotic pressure. How can it affect both for concentration and temperature? That is the absolute temperature on osmotic pressure, which has to be which we can decide it with a Van Hoff's equation for dilute solutions. So for according to Boyle's Van Hoff's law, pi is proportional to C at constant temperature. And for according to Charles Van Hoff's law, pi is proportional to capital T, that is absolute temperature, for a given concentration. So if you combine these two equations, then we can get it pi is proportional to Ct or pi is proportional to CRT, where R is a constant, universal gas constant. Since because C equal to N by V, that is number of moles per unit volume, which we can define it as a concentration. So the number of moles per unit volume is nothing but a concentration. So if you substitute C value N by V in pi is proportional to CRT equation, then simply we can say that it pi equal to N by V into RT or pi V equal to nRT. This is nothing but a Van Hoff's equation for dilute solutions. This is similar with PV equal to nRT. That is ideal gas equation, which we have to be similar with the osmotic pressure, how it affects with volume and temperature, with the concentration and how when the concentration is constant, then we can express the osmotic pressure value, that is pi V equal to nRT. This equation is nothing but which we can call it as Van Hoff's equation of a dilute solutions. So what is R means? Where R is the proportionality constant and has the same numerical value, that is based on the units, its value changes, that is 0.082 1 liter atmosphere per degree per mole, and the significance as a gas constant. Whatever the significance as or which is in gas is constant, in gaseous laws or in ideal gas equation, same thing which has to be in case of a osmotic pressure equation also, or simply Van Hoff's equation for dilute solutions also. So pi v equal to nRT, that is the equation number 4, is generally known as the Van Hoff's equation and holds strictly for dilute solutions. So this is only applicable for dilute solutions, as the solute and solvent interactions are almost negligible in dilute solutions. So what is the dilute solutions means? In dilute solutions, both the solute and solvent, whatever the interactions in between the two components is almost zero in case of dilute solutions. In case of concentrated solutions, these interactions are appreciable and the Van Hoff's equation shows significant deviations. So if they are dilute solutions, the interactions is very less, almost zero. In case of concentrated solutions, if the solution is having a, that is, instead of a dilute solution, if it a concentrated solutions, so the interaction between solvent and solute which is existing, it has some interaction. So there is an appreciable value which we can get it. So the Van Hoff equation, which has a significant deviation from its original deviation, that is pi v equal original equation, that is pi v equal to nRT. So Van Hoff equation relates osmotic pressure pi, volume V, and the concentration of dilute solutions. Just as the gas equation PV equal to nRT relates pressure, volume, and moles of an ideal gas. Same thing for Van Hoff's equation, that is pi v equal to nRT. In that, what it gives the relation means osmotic pressure, volume, and concentration of a dilute solutions, which explains by Van Hoff's equation. And according to equation 3, the osmotic pressure of a substance in solution should be equal to the pressure it would be exert if it were a gas occupying the same volume as that occupied by the solution at the same temperature. So the osmotic pressure for any solution is equal to the pressure of a gas when it's only possible only when same volume is occupied by the solution and a gas, then it is at that too at the same temperature, that is at constant temperature. If the gas, how much it is occupying, that is equal to the volume of a gas solution which is occupied, then only osmotic pressure equal to the pressure of a gas. Next, fourth law, that is for a osmotic pressure, Van Hoff's Avogadro's law of solutions. Like the gas equation, which incorporates Boyle's law, Charles' law, and Avogadro's law, the dilute solutions also obey Avogadro's law. What is Avogadro's law? So like gases, how it can obey the different types of laws, Charles' law, Boyle's law, and Avogadro's law, same thing which is applicable for dilute solutions also. So what it states, Avogadro's law, what it states means equimolar solutions of different solutes exert equal osmotic pressure under identical conditions of temperature. So if the solutions which are having the same molarity or same concentration, but which has a different solutes, if it is there, in such cases, they can exert a equal osmotic pressure. They are having is equal osmotic pressure under identical conditions of temperature. That means if all are in the same temperature, then if solutions concentration is also equal. Only difference is solutes which is present in that solutions is different. But even though different solutions are there, whatever the osmotic pressure which is exerted by the solutions is equal because of equimolar solutions they are, and they are maintained at a constant temperature. So there is analogy between ideal gas and dilute solution. As gas laws are obeyed at high temperatures and low pressures, the solution laws are obeyed for dilute solutions. So which is similar with the ideal gases, or whatever the laws which is applicable for ideal gases, that are similar for the dilute solutions. So all the laws they can be. So there is a analogy which we can observe it between the ideal gas laws with the laws for a dilute solution. So as gas laws are obeyed at high temperature and low pressure, the solution laws are obeyed for dilute solutions. So simply at a high temperature and low pressures, all the gas that can obey the gas laws. The same thing which is applicable for solution, that is obeyed only for dilute solutions. And in the starting of this video, we discussed that osmosis is a one more colligative property. So that what is that colligative property? How can we say that osmosis is a colligative property? That is more important thing. So for dilute solutions, a Van Hoff's equation is pi equal to N by V or T. So for dilute solutions, Van Hoff's equation, that is osmotic pressure equal to N by V into RT, where N is number of moles, V is volume, R is universal gas constant, T is the absolute temperature. From that equation, what it is clear means the osmotic pressure of a dilute solution at a given temperature is directly proportional to the molar concentrations. So which is directly in this equation, if you observe it, at a particular volume, if the temperature is constant, then pi is proportional to N value only. That is, the osmotic pressure of a dilute solution depends upon the number of moles of the solute present in the solution and not on the composition or nature of the solute. So it depends only on N value, that is number of moles of a solute, but not on the nature or the composition, how much it is having in a dilute solution. So that osmotic pressure of a solution is a colligative property. So what is the purpose? What is the main main property of a colligative property? So colligative property is a property of any solution which depends only on number of particles of a solute, number of solute particles, but not on the nature or composition of the solute. Then it is a colligative property. So in case from Van Hoff's equation, if we observe, the osmotic pressure is directly proportional to at constant temperature, which affects only with the concentration terms, that is number of moles of the solute, but not the composition or nature of the solute, so that which depends only on the number of molecules. It is not affected by the composition or by the nature of the solute. So osmotic pressure, once again, it is a colligative property. Next, solutions having molar concentrations will have the same osmotic pressure. If any solutions which are having the same molar concentrations will have the same osmotic pressure. So a pair of solutions with the same osmotic pressure do not involve any flow of solvent molecules through a semi-permeable membrane, and that are called as isotonic or isoosmotic solutions. So a solutions which are having the same osmotic pressure, if the osmotic pressure of the two solutions is same, then there is no flow of a solvent molecule takes place in that solutions, because if the solutions, if they differs in the osmotic pressure, if they are separated with a semi-permeable membrane, then only it is possible to flow the solvent molecules from lower osmotic pressure solution to the higher osmotic pressure solution. But if they are having the same osmotic pressure, then there is no way to flow the solvent molecules from lower to higher. So if any solutions, if they are having the same osmotic pressure, then such solutions, generally we can call it as a isotonic solutions or isoosmotic solutions. If one solution is of lower osmotic pressure, then it is called as hypotonic with respect to the more concentrated solution. So a solution which is having low osmotic pressure is hypotonic, and more concentrated solution, that means solution which is having higher value of osmotic pressure, is said to be hypertonic with respect to the less concentrated solution. The solution which is having less osmotic pressure is hypo, and a solution which is having more, then it is hypertonic. So isotonic, hypertonic, and hypotonic is the three terms which we have to remember. What is the difference between that three? So what are the different types of osmosis process that which we have to know? First one is exoosmosis. Outward osmotic flow of water from a cell containing an aqueous solution through a semi-permeable membrane, then it is exoosmosis. Outside, outward osmotic flow of water from a cell. So from cell, if the water comes out from the cell, which contains aqueous solution through a semi-permeable membrane, then it is exoosmosis. Example is an egg after removing hot shell placed in concentrated NaCl solution is called as exoosmosis. So when we place an egg in concentrated sodium chloride solution, so then a solution which has to be flowed from a semi-permeable membrane. Endoosmosis, the inward flow of water into the cell. So water has to be entered into the cell containing an aqueous solution through a semi-permeable membrane. Example is an egg placed in water is called as endoosmosis. So in such case, water has to be flowed towards water if we place the egg in water. If we place the egg in sodium chloride, water from egg, it has to be moved towards the concentrated NaCl, that is exoosmosis. That is the main thing. Next, reverse osmosis. When a pressure higher than the osmotic pressure is applied to the solution, then the solvent from the solution starts flowing towards the pure solvent. So when we apply a high pressure higher than the osmotic pressure is applied to the solution, then the solvent from the solution starts flowing towards the pure solvent. The process is called as reverse osmosis. So we have to apply some pressure to continue the osmosis process. That means flow of a solvent from the solution. That is nothing but a reverse osmosis. This process is very useful to get pure water from seawater. That is main application of that. When a pressure higher than the osmotic pressure is applied to seawater, pure water from the seawater passes through the semi-permeable membrane and impurities are left behind. So the same thing which is implemented in the water purifiers also, that which we can use it in our household applications, like any instrument. If we implement the reverse osmosis process, then we can get it the water in the pure state by simply removing the impurities in that. How can we measure the osmotic pressure in the laboratory? Generally, we can use it a Berkeley Hartley's method for to measure the osmotic pressure. So this is the best method for the measurement of osmotic pressure. The method is based on it is the best method for the measurement of osmotic pressure. The method is based on applying sufficient pressure on the solution side in order to check the osmosis. So this is the best method, even though many methods are available, but this is the best method for to measure the osmotic pressure. So what we have to do in this method is simply we have to apply the sufficient pressure on the solution side in order to check the osmosis. If we apply some pressure on the solution, then automatically solvent molecules are ready to flow from the solution through a semi-permeable membrane. So it consists of a porous part open at both the ends. The porous part has copper ferrocyanide membrane, that is nothing but which can act as a semi-permeable membrane fused in its wall. It is sealed into an outer bronze cylinder filled with a solution under examination, and water is taken into the porous part. So we have to separate the solutions with a container which is having two compartments. In the two compartments, we have to use that two compartments has to be separated with a semi-permeable membrane, that is nothing but a copper ferrocyanide membrane, and it has to be sealed out with bronze cylinder fitted with a solution under examination, and water is taken in the porous part. So the bronze cylinder is fitted with a piston on which weights can be placed to exert pressure on the solution. So when bronze, that cylinder which has to be fitted with a piston, from that only we have to apply some pressure. This is the actual instrument which we have to use it in Berkeley and Hartley's method. So in these two compartments, these are there, and this one which we have to insert the, so that is the level of this part which we have to observe it. And then this is the semi-permeable membrane or a simply porous part which has to be, that is prepared with a copper ferrocyanide. And this is once and this has to be, when we apply some pressure using this piston, then whatever the molecule, these two solutions, and this is in between, this is water is there. When we apply some pressure, solvent molecules that has to be moved towards the water because which is having a low concentration. With that, we can observe the water tends to pass through the porous part towards the solution. So because water which is having low concentration, so now it is ready to move to the solution. Now pressure is applied with the help of piston so that the water level in the tube becomes stationary. So which we can observe the level of water here, whether it is same level or is it is going to be decreased or increased. This external pressure applied on the piston is equal to the osmotic pressure and can be read on the manometer. That which we have to measure in this place, we have to connect it a manometer. There we can observe the how much pressure which is applied by the piston. That is nothing but the osmotic pressure. So in general, osmotic pressure up to 150 atmospheres has been measured accurately by this method. What is the main advantage of this method is, in general, we can measure the osmotic pressure up to 150 atmospheres. We can measure for any substance using Berkeley and Hartley's method. So that is the main advantage of a Berkeley-Hartley's method. Then what are the advantages of the method? It is less time consuming. So basically the method is which takes only little time to perform the process, and the equilibrium is established quickly and hence results are obtained in a short time. So movement of solvent particles, that is flow of solvent particles, takes place very fastly, and so the equilibrium which is existing between the two solutions, so the results which we can obtain in a very short time. That is the one advantage. And second one is the concentration of the solution does not change during the determination of osmotic pressure. So when we measure that osmotic pressure, a concentration of a solution which won't be changed in this method. There is no strain on the manometer and the danger of breaking of manometer is eliminated. So because we are maintaining the same concentration, so the concentration is not going to be changed. So if we change if the solution concentration changes or if any pressure takes place, that will be effect on the manometer. So it may be breaks. So that which is not possible in case of a Berkeley and Hartley method in this case. Vant have deduced the loss of osmotic pressure. So he only deduced the osmotic pressure loss. He showed close similarly between gases and the dilute solutions. According to Van Hoff, there is many similarities between gases and dilute solutions. So only he proposed different laws, whatever as a particular gas can obey, the same laws which he explains on osmotic pressure for a dilute solutions. That is another thing. So how can we estimate as it is a colligative property? We can find out the molecular mass of a solute or a solvent using osmotic pressure. That is main applications of colligative properties. We can easily estimate the molecular mass of either solute or solvent using a colligative property. So osmotic pressure itself is an colligative property. So we can easily determine the molecular mass. So how can we determine the molecular mass using osmotic pressure? That which we have to know. So for dilute solutions, it is found that the equations, that is pi v equal to nRT holds good. So for dilute solutions, generally pi v equal to nRT, that is nothing but Van Hoff's equation. It is good for dilute solutions. In place of 1 mole of a solute present in V liters of the solution. So 1 mole of a solute, if it is present in V liters of a solution, let small w grams of the solute, whose molecular mass is m dash, be present in V dash liters of the solution. So in general, for pi v equal to nRT, 1 mole of a solute has to be present in V liters of the solution. Instead of that, if W grams of a solute, if it is present in V dash liters of a solution, then the same equation which we can represent it as n equal to number of moles of a solute, so that n equal to weight by molecular mass of a solute, so that is nothing but W by m dash, which gives to number of moles of a solute. And V dash equal to V in case of for a solute which is having W grams weight and m dash molecular mass which is dissolved in V dash liters of a solution. So that V dash equal to V. So same equation pi v equal to nRT, which we can replace it with, instead of V dash and m dash, then simply we can write the pi v equal to nRT becomes pi v dash equal to small w by m dash RT. So m dash equal to, that is nothing but molecular mass of a solute equal to WRT by pi v dash. So if you know the value of osmotic pressure pi and the value of molecular mass m of a solute can be calculated. So W is weight of a solute, we know. R is a universal constant, that is also we know. T is absolute temperature, that is how much temperature we are going to be maintained for a dilute solutions when we perform the osmosis process, that also we know. And V dash is volume of a solution, how much it is going to be dissolved. A solute can be dissolved in a particular solution, that is also we know. So using this equation, m dash equal to W or T by pi V dash, we can easily find out the molecular mass of a solute by osmotic pressure, as it is a colligative property. So this, which we can say that using this, what is osmosis, osmotic pressure, how can we calculate it, and how can we express as it is a colligative property, how can we determine the molecular mass of a solute using osmotic pressure as it is a colligative property, that which we discussed in this video. We can continue in the next topic in the next video.